然后他们是说用这个好像比较好养。
你这样子全部都录得到吗？再看一下。
但是好像要等一下它才会跳出来。因为它这边是说在直播。看一下。
这样声音是 OK， 测试 OK 吗
？OK，还蛮干净。
好，谢谢。
梦的期待太伟大。
没有，我跟他讲说，
每次课程都有不一样的吃的。
我刚刚给他看我奶奶97岁的视频去爬山。
哦。
97岁啊。
哦。
对，而且我没有我妈那么伟大，我妈随时会变坏心。我都不太变坏。
这是第一。
那是我那天跟他聊天的时候，他说他妈都会喝那个，我说那我
知道。
对，我想知道他妈都喝什么。
你这么优良的基因不打算传下去吗？
我跟你讲，他们最近问我，不是他们最近问我一个问题，他们最近问我一个问题，我都很尴尬。我回家的时候，他们就说：“你毕业了没？”每次都问我毕业了没，然后我就说：“ 就不好说，每次都问我毕业了没，而且问我觉得生女儿是对的，虽然你生2个，然后我们家生4个，因为母亲节的时候儿子都不见了，然后只剩女儿跟妈妈都很孤单，就是妈母亲节快乐，没有，真的，然后我妈就会说，我就是说，哎。那个，然后他就那种我妈那种很内敛的哦，就是那种很淡定的。我说，然后他说你那么远，我说不会，我每年都一定会飙过来帮你送蛋糕。我妈就这样很内敛的，然后她一直在等儿子出现那一刻，然后我就是在等，然后就想说要帮我大嫂买一下母亲节礼物，为了我被我姐训练到都很周到，我就跟他们讲说我的母亲节礼物是。我前2个礼拜先去台中陪我姐过生日，因为她是我另外一个妈，就台中的姐姐，我都叫她妈，就是我都叫她理化老师。然后我回去给我妈过母亲节的时候嘞，我妈很孝顺，前3天就先帮我阿妈过母亲节。哦。对，要先帮我阿妈过，我阿妈是会生气。真的。我阿妈很凶的，真的，都骂我们比任何老师还凶，真的。你不要看她97岁这样子哦，记忆力很好。真的，而且他吃什么、啊？如果你偷吃他的饼干啊，他会生气。真的？真的，他会骂人。然后你买过什么给他好吃不好吃，他会记住。都记得。对。他的兴趣是喝沙士跟可乐，还有吃炸鸡跟蛋糕。
哇，这样还活到97，厉害。
对啊，他真的，而且他没有吃就会生气，而且你今天讲，你明天没有去买，而且他要去烫头发哦，要 settle 去我阿姨家 settle 4点，然后我妈就说97岁烫什么头发啊？你不懂啊，我100岁都要烫。你怎么了？
而你讲了这么多，你还是回避的问题。
我没有。
我又回来了。
我不是，我要讲一件事情。
我记得去年在交大游泳池遇到你的时候。
我是在复健，我昨天又去了，你知道为什么吗？为什么我去？
你是复健心理吗？
不是，我要讲这个，就是我之前做那个周志远那个案子，是我下赌注的，因为没有人愿意让院的杰出教学这样做，就是只能拍校的。可是我就校就一直找不到名单啊，所以我就说我要做院，然后院我就那时候选的周志远跟李奎允。然后做的时候其实案子很大，因为其实大家就说，如果你再找不到校了，我就要放弃，就是不要再选校，全校老师都选。我就说不行，我要开院的，因为李美惠交代我一件事情，他就说这个案子是他接的嘛，97年推的，他跟潘晴才跟那个，他就说你一定要选校的老师，记住无论如何一定要选校杰出，因为有一天清华的这一些能控管，就是帮清华变很强大的，就是这些校杰出的老师，因为一定会有一批是教学跟研究很厉害的。他说你现在可能看不到，然后他就规定就是可是我就一直找不到人。那时候他们就说，如果你再找不到人就要释放。那我做周志远的时候，我就必须要在很快的时间翻身，我必须要2个月内翻身。所以我那时候就一直加班。然后我上一次就是我不知道那天那个红台梯吧，我就在那个门口骑脚踏车，我就摔到这个，然后我就不能动啊，然后后来就开始复健，对，后来我就想说不一定，所以那一天那个量体温的时候，周志远看到我啊，我就说我们2个是一起长大的，我们从院杰出教学奖得到校杰出教学奖。我写那个感言的时候啊，我不是写那个单子给他吗？我都说我一路看你长大，我说你爸那里我也有记了什么的，然后我就说我从你这样子到这样子。
可是他爸好像没拿过校，儿子拍的。
他爸没有拍啊。
他爸不是拍了摩克斯吗？
没有啊，我是跟他爸的好朋友。哦。他爸的好朋友就是另外一个老大，我跟那个老大就一直工作。对啊，没有，那时候就是一直找不到人啊，然后我找的人都拍光了。就没有人啊，新的人被我发到又很紧张。上次有一个老师新人被我发到，他说我怎么了吗？我说你没事，就那个化学化工嘛，化学化工都没有。 王姐好像是下学期，是那个他们找的。
王姐好像有拿到校结束。
有，她好像会是下学期吧？她蛮活跃的。
王姐现在是你们教务处的人。
我知道。
对啊。
她是后来才是的，其实很早就那个了。
很早，其实陈荣顺早就已经内定好他了。
对啊，王姐。像有一些就完全就一门都没有，没有啦。我觉得可以跟谁合作，就是运气，真的，你就是我的运气。这学期最大的运气就是他，我是讲认真的，我这辈子运气都用完了吧
？OCW 其实对老师的负担不大，因为其实就是正常上课。
没有啊，有的老师负担很大，一看到我就有压力。
正常上课录起来，其实感觉还好。
没有，那是电资院老师比较本来就教得好，连院的都教得很好，对。可是像有一些他就会压力比较大，因为他有一些的给分啊，或者是班级比较小的。可是之前都是胡慧文小姐找的，所以那个什么赵启超、高淑荣、赖志煌、李秀煌，那都是胡慧文找的。后来胡慧文就说他后面是正光嘛，然后正光就觉得压力很大，他搞不定这些老师。然后我是到了前3个月之后，我就是先跟那个几个老师合作，其中有一个是李敏，他就说你跟李敏很合拍，我就说我们都是直白路线，就很直白啊。后来他就在那个任内的时候，他就找了我第一个合作电机系的，应该是赵启超啊，黄眼界是他找的。
黄眼界也录过电磁学。
对，那个是慧文姐找的，全部都是慧文姐找的。
最近还有电机系的老师问我说，为什么黄眼界的电磁学也是英文的，为什么还要再录一次？
我们很多课会再重新录，因为太旧，外面的 feedback 都是太旧，所有的课。
黄眼界我印象中没有几年了
，100年录的。我现在还在翻新97年的那个潘芹才老师，他们网站我都帮他们弄得很漂亮，因为我想要整个翻版，那个都很旧了。而且我们学校就是一门课录完之后就不再录另外一门，对，对，没有啦。我的任内我觉得应该，如果我觉得学生的意见是好的，就像他们叫我一直录叶明权啊，材料力学。
叶明权他还愿意录吗？
他录完了，而且他到澳门大学，立生说到澳门大学还看到我的海报，他觉得莫风好可怕啊。我说他到哪里我都要寄到哪里啊。
还有2分钟。
对啊。我如果有一天嫁出去，一定会把饼送给你，可是怕没有这个嫁不出去了。我是讲认真的。有听到吗？我会送给你们的。我妈就说我自己去买比较快。他们来了吗？这种东西是所有人的疑惑，对，我不知道怎么会这样。上一点，看到老师的头，故意的，看到，这么安全，对，放大吗？这样子对。
Okay, let's begin. All right, so welcome back to the class. Last time we spend a lot of effort trying to understand magnetic flux density, B. So basically, B is a vector field, and it is defined as the flux density. So somehow this equation should be quite familiar to you. This is called the Ampere's circuital law. It tells you in the integral form, right? You have a closed loop integration. So inside that closed loop, you might have some flux density, and you integrate along the differential path. So totally, you will know how much current is being enclosed by your closed loop. So this is extremely useful. So today I intend to show you how to use this simple law. The first example is in your textbook, the very first example in this chapter. So you have a very long wire. So the length of the wire is assumed to be infinite. And inside the wire is metallic, so you can conduct current. Point by point, you have the same current density, right? So the entire wire conducts a current of I. But inside it, point by point, you have the same current distribution. So this is for simplicity, only just to show you how to use the Ampere's circuital law, right? The wire has a radius of B, so we want to use this simple formulation to find the resulting magnetic flux density everywhere. Whenever you hear the wording everywhere, you have to ask yourselves, well, given this wire geometry and you have the closed loop, somehow you have to divide space into two different regions. One is where your observation point is inside the wire, meaning your radius. If we use cylindrical coordinate, it's the easiest coordinate to use, right? For a wire, it represents a cylinder, right? So if the radius is smaller than B, then we are trying to evaluate the B field inside the wire with a given radius. Here on the textbook is R1. But when you are outside of the wire, meaning you form a closed loop with a radius R2, and here R2 is greater than B, you are trying to evaluate the B field outside of the wire. So how can this truth be different? The major point is in the current encompassed by the closed loops. What we know is over the entire wire, we have a steady current of I. So which means when your R2 is greater than B or equal to B, whatever closed loop you form, you encompass the total current I. But the major problem comes to when you are evaluating a closed loop inside the wire, meaning R1 is smaller than B. In this case, the total current encompassed by this long dashed circle is only a fraction of I, right? And therefore, you have to take into account of this I. It is only a fraction of I when you are inside, all right? Therefore, we have to analyze this simple problem, and we divide into two different regions when the observation radius of your closed loop is smaller than B. When you're smaller than B, fine. it does not affect your closed loop integration. Due to geometry, symmetry, we know that B, we assume the current is flowing into your eyes. So basically we know the B field lines are closed loop, right? Just in the direction of your loop. So all you have to do is 2 pi r times B1. That is the total closed loop integration. Because B is also in the phi direction. Here we're assuming the current is flowing in the z direction, right? So the B field lines are oriented in the phi direction, parallel to your differential length. So the closed loop integration is a direct multiplication to 2 pi r. So this is without any question. There's no doubt. But the question is, what is the amount of current being encompassed by this closed loop? Well, we can only assume we have a very uniform current distribution. So therefore, when your radius is smaller than B, it takes a proportion that is depending on the area, okay? So for the small circle, we know the area is pi r squared, and we have to divide pi b squared and multiply by I. That's the fraction of current enclosed in my loop. This is only true when the current density is extremely uniform, right? Therefore, the total current encompassed is I, the total current, multiplied by the ratio of the radius to B squared, right? So in this case, when we are inside the wire, we know the magnetic flux density is everywhere in the azimuthal direction, in the phi direction, and the quantity is proportional to your radius. Okay? So this is when you are inside the wire and your distance by r from the origin. Second case is easier when we are outside. When you are outside, your r, the radius, is greater than b or equal to b, then there's no question. No matter how big your closed loop is, the total current encompassed is the same. It's just I. So in this case, very simple relationship. Again, the flux density is everywhere in the phi direction, but now is inversely proportional to the distance of your observation point to the origin. Together, this is a simple plot for you. If you have an infinite wire with a very uniform current density, then the magnetic flux density inside is linearly proportional to the distance and then is inversely proportional to the distance. Right? And this point is at the wire radius. This is a direct usage of the Ampere's circuit law. Right? All you care about when your geometry is simple, your current distribution is uniform, you can invoke it, you can find your resulting magnetic flux density easily. Let's take a look at another example. This is some device quite often used in daily lives. Okay. If you open up the case of an amplifier, you always see this type of solenoid. Okay, it's called a solenoid. Solenoid. But to properly invoke Ampere's circuitous law, again, we are assuming the solenoid is infinitely long, right? So how to fabricate a solenoid? You have some core, okay? You have some core, and you run the wires, the conducting wires, turn by turn. And then you have a solenoid. And we used to use this "and" to define the number of the wires rounded per unit length. Okay, it's just the wire density. Okay? In this particular case, current direction is given flowing from the bottom to the up. Alright? So at this point, although we do not know the amplitude of the B field, we should have a clear knowledge to the direction of the B field. Okay? So for each run, the current is flowing from the bottom to the top. So that means on the top, if you draw the cross sections, like I did, I'm drawing the cross section of the solenoid. Over on the top, you have current flowing into the board, right? Current is flowing from the bottom to the up, which means in a rounded wire, you take the cross section. On the bottom, you have current going out, and on the top, you have current into the board. Okay? So this is the cross section of this solenoid. And now it's up to you to decide where is the proper direction of the resulting B field. If you still remember, we use the right-hand rule. Okay? So in this case, your forefingers are used to denote the direction of the current. So the direction of current is flowing from the bottom out of the board and into the board on the top. Okay? So you use your right hand, you have to bend it, of course. So you follow the direction of current using your forefingers, and your thumb points in the direction of the B field. So in this case, following this current direction, I know my B field must be pointing from the right to the left. Okay? And following the current, therefore my thumb points in the direction of B. Okay? So one thing you have to pay attention. Every time you're trying to analyze for B field, well, you're looking for a current. But current has certain specific direction. And that current direction is going to affect your B field direction. Right? So at this moment, if I define my Z coordinate, Z being positive, pointing from the left to the right, immediately you have to remind yourself, B field is pointing in the negative Z direction, right? Because using your right hand rule, you know B is in the negative Z direction. Okay. All right, so that's taken care of. Now we want to know the quantity. We want to quantify B. So how to quantify B? Well, this circuitous law tells us we have to form a closed loop. And then we try to evaluate the B dot dl over this closed loop. And we also ask ourselves how much current is being encompassed within that current. That helps us to quantify the value of B. So in this case, we have a very long solenoid. We want to form closed loops. Right? Over the past few years, I realized students have problem in forming the closed loop. Right? So in a simple problem, there are three potential ways to form the closed loops. So one is the closed loop is somewhere inside the solenoid. We call this the solenoid, right? Outside you have free space. So some students would just try to form an arbitrary closed loop inside the solenoid. Another student, the second student, might form a closed loop in a vacuum. And a third student would form a closed loop denoted by a black dashed rectangle. So this is telling you, even though the circular law is extremely simple, but you have complexities, right? Just in how to form the proper closed loop is demanding on your understanding. Okay. So let's take a look at the two blue loops, A and B. Does forming the closed loop inside the solenoid make sense? Does it make any sense to use this one or this one? Well, first of all, let's look at this one, okay? If we use this closed loop and we want to use this guy to implement Ampere's circular law, is it meaningful? So let's come to the blackboard. Over on the blackboard, I formed this closed loop, B. Okay? So I have defined its width to be delta W. I'm making the height extremely short, so I don't evaluate any B component in the y direction. Okay? I'm only evaluating the z component. This closed loop allows me to write this is equal to B2 delta W minus B1 delta W. Right? Because my loop direction reverses sign as compared from the bottom to the top. So on the bottom, this loop direction is parallel to the bottom segment of B. But the top direction is reversed, so I have a minus sign. Right? But then the problem is, what's the amount of current being enclosed by this loop when you're outside of the solenoid? Nothing, right? On the right-hand side, you're supposed to evaluate the amount of current encompassed by your loop. So unfortunately, when your loop is outside or inside, you don't really encompass current. Why? Why not? If your closed loop is inside, basically you don't have current being encompassed, right? And also, from this relationship, it does not give you any meaningful result. This is only telling you B1 is equal to B2. Okay? But still, even though when you define the closed loop outside or inside, it's not meaningful. But they both tell you B1 is equal to B2. Can you try to justify that result? Or let me try to change the question. If on certain examination, I specify I want you to use closed loops A, B, and C to evaluate the B field, the flux density. Ideally, you use both A and B. You would come up with the result B1 and B2 are equal. B1 and B2 means the flux density on the top and bottom segments. Okay. But then you have to think. B1 equals to B2, it's not giving you the end result that you desire. Because in the end, when we invoke this law, we want to know how to quantify B. But up to now, using both these two closed loops, you only have B1 equals B2. So what is B1? What is B2? You don't know. But what's the message you have learned? Whichever step we take, we always leave some trace. 反走过必留下痕迹. A very nice translation, right? So each step we're taking, we're leaving some traces. So even though we chose the wrong closed loop to start with, to work with, but somehow they both tell us B1 equals to B2 means when you really have an infinitely long solenoid, the B fields inside can be treated as a constant. The B field outside can also be treated as a constant. That's extremely meaningful, as to my personal opinion. So this is telling us inside, we can say this is B in everywhere, because you are free to determine where this closed loop is, right? But inside it, it's just having a constant value. And outside, everywhere, it's a constant. Okay? I know probably each and every one of you analyzed this problem in high school. But the high school teachers will only tell you, well, in trying to solve this question, you have to assume the field outside is 0 and inside is a constant. But you never asked why. But now you know why. Because now you have a full understanding to this circuit law. Okay. So to me, the necessity of closed loop A and B are so important. Because before you use this closed loop C, you have to have prior knowledge to what type of field distribution you're dealing with. In this case, because the solenoid is so long, the length is infinite, therefore making the inside to having a constant field. Field inside is not position dependent. Field outside is also a constant. Here is having a value, here is having the same value, here the same value. Alright? So you have to know these two informations before you can proceed to using closed loop C. Now we turn to closed loop C. Okay. Inside it, we have a constant field amplitude called B. Outside, so we're trying to evaluate these two segments. So here, I know the length is L. So I have a constant field inside. So this B in times L, ideally minus B out times L. But usually we just write this one. Why? You will be very surprised. I'm spending so much time on this simple example, which everybody knew it or learned it starting from high school. But as we unveil the reality, probably you realize how much details were being omitted in the past, right? In the past, you just write down this equation. Everybody knew how to write down this equation. But how to justify this equation is correct. And that requires your deep understanding. The reason we can just write BZ times L is BZ is B inside, B in, right? B in times L, that is your line integration, equals to this quantity. Well, this quantity is direct and straightforward because whenever you have the length L, you know your wire density. N times L and times I tells you how much total current is being encompassed by your closed loop. But the real trick comes from the left-hand side. Why? Because, well, whenever we have a closed loop, if we don't care about these two y-oriented segments, aren't we supposed to also evaluate the path integration of the top segment? But here, it's not visible. So here comes the truth. Well, I mean, refresh your memory. In the past, we romantically just assumed outside of the solenoid, we have no field line. So the flux density is 0, right? TA, is it true? I mean, in the past. All the teachers, all the professors just tell you that. But in fact, using this closed loop, B, in my PowerPoint, we only have the result of B1 equals to B2. So it only tells you outside you have a constant field. But no word is telling you it is equal to 0. It is constant everywhere, but who decides it's 0? Can anyone answer that question? From our detailed analysis, field outside should be a constant, not spatially dependent. Field inside also a constant. Point by point, they are the same. But somehow, in the past, it's a custom to say that outside of the solenoid, the B field is 0. And because B field is 0, so you know the B field inside the solenoid, right? Something minus 0 is equal to the total amount of current encompassed. So can anyone tell me, this is a challenge to the students, how can we just romantically say this is 0? Well, if this is not 0, let me tell you the ugly truth. If the field outside, well, it's a constant, right? But it is not zero. You don't have a way to quantify the field inside, right? If you use loop C, all you have is B in times L minus B out times L is equal to mu 0 and L out. The ugly truth is, well, if you really use closed loop C to perform the evaluation, this is what you get. You have the field inside the solenoid minus the field outside the solenoid is equal to the total current encompassed. So you still cannot quantify either of the field. The only way you can satisfy yourself and write down a beautiful answer and hoping that you can get score is you say this is 0. And therefore you can quantify. But you have to tell me, I mean, what's the reason behind this beautiful no field outside of the solenoid? I'm getting you to think, right? Finally. So you should watch the video, the streaming. The problems we're working with are extremely impractical, extremely ideal. So the magic word comes to infinite. Currently, we're assuming the solenoid is infinitely long. Okay, infinitely long. What does that tell you? And it's a real test to your understanding to how the B field look like. Okay. As I stated, the B fields form a closed loop. So somehow inside the solenoid, the amplitude, the magnitude is a constant, which is fine. I have no objection to that. But somehow when you, well, at a certain point, your solenoid has to end. So basically, your field line forms a closed loop, right? So think about it. This must be true. Inside the solenoid, you have very constant B field. But each field line needs to close upon itself. So if you really draw out the resulting B field lines, how can you say when you're outside, you have no field? Think about it. Can anyone answer? I mean, I have 3 filming crews who are all in the sophomore or junior year. I have the TA who is a master's student. Can the 4 of you answer this question? Apparently, what I'm trying to point out is apparently we're doing something wrong. Because apparently, magnetic field lines close upon itself, so each field line you have inside must have the corresponding field line outside. But somehow in our derivation, we just assumed there's no field outside. Under this assumption, we can quantify the field inside. This is really weird. Okay? So anyway, when you're receiving a test problem, okay, not from me, you write down the so-called right answer. But if you are on a test, examination in my class, I'm more than happy to see your challenge to this simple problem. If you can write down all your reasonings, this is wrong, how the answer should be adjusted or modified, I'm more than happy to see your rebuttal. Okay? So what is the secret behind this answer being correct? It has been there for over 100 years. And all the professors just give you the points when he or she sees this answer. So this is the point where you have to understand for each individual problem you're given, you are bounded or you're luckily spared by assumptions. Infinitely long solid weight. So under this assumption, this impractical perfect assumption, you are allowed to say that there's no field outside the solid void, even though you know the fact B field lines closed upon itself. Why? When the solenoid is extremely long, which also tells you your observation point outside the solenoid is very close to the solenoid. Okay? So this is telling you, well, okay, I have a closed loop B field outside of the solenoid, but compared to the distance. For example, this is Earth, right? The solenoid is the core of the Earth, and we are at the surface, and this field line is somewhere at the sun, right? So the distance between the Earth to the sun is so long. Basically, all the fields are penetrating the sun and not Moon, not Mars, not Earth. And therefore, we say, oh, here, outside, there's no field line. Okay. What I want to show you is in practice. If you have a finite length of solenoid, don't ever think about using Ampere's circular law to find the resulting B field strength. Because when your length is finite, as you can see, right? When your length is finite, all the fields closed upon themselves. So basically, you do have field immediately outside of the solenoid. So in this case, you form a closed loop, you have to evaluate B inside minus B outside. They're both unknown quantities. So what do you gain? Nothing. So the current case we're trying to analyze is more like this case, right? This case is having a quite uniform B field near the core, and it does close upon itself, but it's so far away. So this field line is not penetrating across this point, right? So the difference between a finite length solenoid and an infinitely long solenoid is when you increase the length of the solenoid, you're trying to remove all this so-called near field flux densities. So in a far field, when you're very far away, you do have fields. But when you're close to it, you don't have the field lines. And all the field lines are concentrated inside the solenoid. Okay? Now think about it. This is very profound. Because it's very profound, I'm spending 20 minutes to talk about it. Right? So think about the need to form A and B loops. To me, your ability to form the A-B closed loops is a winning key to understanding this simple problem. Right? Actually, I mean, if you have a finite length, you form a closed loop inside, you know the B field at this point will be different from this point. Okay? So each problem, I welcome you to challenge the end result, but you have to come up with a proper explanation why you have your challenges. Right? Okay? Oh, by the way, this picture is extremely profound in a way that if you think this problem as a boundary value problem, the B field lines close upon themselves. But if you view this as a boundary, okay, what do I mean by the boundary? Boundary, right? Two different materials forming an interface. So if you have the field line coming in, somehow your output field line is, so this is B inside and this is B outside. I'm trying to attract your attention to this particular closed at the interface. Your B field line is coming in with certain angle, and your B out is here with certain angle, but they are both on the same side of the surface normal. Now think about it. This is a very unique capability only seen in magnetic fields. So as your examination is coming up next Monday, everything in E field, you have a field coming in, right? D field, and you have a field coming out, D out. In the world of electricity, the boundary values will always require the input field and the output field are on the different sides of the surface normal. But here in the world of magnetism, well, input field and output field are allowed to be on the same side of the surface normal. This is interesting, weird, and I want to challenge you to finding out why. What is the difference that allows magnetic fields to appear on the same side when you consider a boundary value problem? Okay? And I promise you, the final examination, there will be one problem appearing about this issue. Okay? So this is a real understanding to the difference between E field and magnetic fields. Right? So I propose we stop here. We take an early recess of 10 minutes, so we come back and continue on the next subtopic. All right, so let's take a 10 minutes rest, unless there are students having questions online. Nope? All right, let's take a 10 minutes recess.对，这个就更诡异了，因为这样你 total current 是零，
对吧？那
对
这样外面不就是零了吗？
可是这没有，你 这样包，你得到的还是这个数学式子啊。
没有，不然你里面你本来就没有电流，所以你市场应该是
对，问题是，你这个时候只是把它的方向，你这个时候会算到理论上这个时候应该会是 B2 的 delta W 加上 B1 delta W 等于0。你只是得到这两个相等，还是相等，方向颠倒 ，magnitude 相等，对不对？你 total 的 current 是0，但因为它的电流方向跟它正好颠倒，所以它们两个的场的方向颠倒，所以不管怎么样都是相加的。那你得到这个东西是 B1 等于负的 B2，还是一样的 field strength。其实这个题目你仔细去想安培定律无法帮助你任何东西，对不对？你仔细去想的话，假设今天你是 finite length，这条公式根本没有用，所以必须要回到我们下面，就要用 BO 沙法，你只能用 BO 沙法乖乖的去算。
那如果说因为它是无限长的话，那相对来说，基本上如果无限长，代表说这个很近，可以这样想。
是，对啊，这是我的意思啊。
所以就是说，那我这个 delta L 是很小的，那所以说，如果是用这样是用 BO 沙法去想，
还是用 BO 沙法？所以就是说，安培定律对比到电学就是高斯定律。
对，
高斯一定要题目有一些很漂亮的几何对称性，或者很长或什么东西才能用。不行的话，你乖乖用库鲁。
对。
BO 沙法对应到电学里面的库鲁。安培对应到高斯。你有这个题目很好啊。所以这个题目过往反正大家每个老师3分钟就教完，外面等于0里面是 constant， 然后你就这样算。可是我当学生的时候，我就认为，为什么大家都可以这样讲？是没有人跟你说外面一定要有0啊。那为什么里面是 constant？ 里面是 constant， 你这样子在里面form一个 loop， 会强迫你说两个相等。可是我们回到这个 finite length， 那就不对了。finite length 的时候，那你说两个还是相等的，不可能。所以安培这个 circuital law 是有很多的问题。所以当你选择要用或者用高斯的时候，你要看到你的题目，你对你的题目要很理解，说这个题目可以用这个，不会有问题。所以我今天想要呼吁的是说，大家笨笨的这么用，你有想过你今天为什么可以用吗？对不对？就你说的很好啊，你form一个 loop， 如果有学生问这个问题，我觉得很棒，可以加。你form这个 loop， 你就没有任何的电流，那你理论上推出了什么？你想要得到的目的是 outside 等于0，目的是没有这一回事，没有任何一条公式会告诉你 outside 等于0，因为 outside 本来就不等于0。因为磁场必须形成封闭回圈，不可能里面有场线，外面没有。所以或许我考试应该这样考，请你们用各种方法去证明外面的场等于0，大概是不可能。所以电学跟磁学最大的差别在于，磁学形成封闭回圈，所以不可能有一个地方，不可能有个 device 说它的外面的场是等于0，不可能，是 impossible。你只能说你躲得很近的时候，你感受。
这就是等于说是磁单极的问题。
磁单极，
因为如果你有磁单极，又有可能外面是0，里面是0。
Yeah。
就等于说是。
可能可以这么说啦，问题是磁单极这个东西，现在有人说有找到磁单极啦。
对，但是我是没有谁看他是怎么做。
对，他在低温的时候。
有人说他找到它是一个就是 fake 的假象。
对我来说，那个不太有意义。那如果你真的有磁单极，就在 divergence of B 不等于0。那 divergence B 不等于0，在纯数学的世界里面是可以推导出很多后面的现象。
因为它这样子行为上就跟电场是
一样的，问题是他们其实就不一样。
对，就是你没有单极的问题。
是啊，所以我个人是我不知道这些人当然除了出 paper 之外，到底有没有去挑战过自己说，你 proof 有磁单极之后，可是明明你知道场的分布就是不一样。
这次录影的确，我觉得把这个部分录得比较透彻。真的，每一次我上课之前都很讨厌上课，上完之后就觉得很喜欢上课。
Alright, welcome back. Now we're moving on to a new territory. Before we move on, as reminded by our wonderful TA, I think it's very nice to let you know the comparisons, the differences between the E field and the B field. So this one is called Gauss's law, right? If you still remember, we also covered Gauss's law and we calculated the E field intensity pattern by invoking Gauss's law. Now, we also introduced the Ampere's current law, circuitry law, right? And we just showed you two different examples. But if you think back, whenever you want to invoke Gauss's law, I particularly mentioned your given problem has to show certain type of simplicity in terms of geometrical symmetry, or you have very uniform charge density, Otherwise, you have to use the Coulomb's law, right? Coulomb's law is a tool where you don't have full insight to your problem. You only know your charge distribution, charge density distribution. You just sum it up over the entire volume, right? So in direct comparison, when we march into the fields of magnetic vector fields, even though we have a very simple rule taught by Ampere, if you have some current density, ideally you would produce magnetic fields. But this equation, as I just showed you previously, if you want to use it, you also need to have very deep understanding to the problem you're trying to investigate. You have to have some impractical assumption of infinity length, uniform current distribution, geometrical symmetries, right? So then the question now is, well, if the current density is not a constant, your geometry is not symmetric, do we have also a tool like the Coulomb's law for electricity that can permit a straightforward calculation of the resulting B? All right, so that's an entire purpose for the following 15 minutes. Right? Again, using Gauss's law for electricity, Ampere's law for magnetism requires your deep understanding. If you don't have the confidence to invoke these two laws, well, we want to have direct, messy, but brutal force integrations. So luckily, in electric fields, we have Coulomb's law. But up to now, in magnetic fields, we don't know how to do it, right? And that's the entire purpose, the meaning of introducing a vector magnetic potential, right? The definition comes from vector null identity. Well, if you still remember, if you have some vector field, and you take its kernel, is not equal to 0, then you're resulting, after the kernel operation, you're trying to find the circulation, right? And therefore, if you have circulating field, the field closes upon itself. Then you take its divergence, it must be 0, right? This is the meaning behind this null vector identity. But coming from our basic postulate, when B fields are vortex fields, all the B field lines close upon themselves. Therefore, divergence of B equals to 0. And the physical meaning is we cannot easily find an isolated basic element to produce B fields, right? You don't have an isolated independent source. But if we compare these two equations, well, can we say that because the B field is a non-conserved vortex field, so its divergence is always equal to 0, but at the same time, we know the null identity divergence of a given vector is equal to 0, then this vector field itself can be defined as the curl of another vector field. So what about this? So basically, B, our magnetic flux density, can be defined as the curl of another vector field. And this vector field we define as our vector magnetic potential. So up to now, everything is just mathematical. So later on, I'm going to show you the physical meaning of A A, and I want to show you by introducing this new quantity actually allows us to finish the task. We can come up with a new law so that even though your current density is not uniform, but it allows you to directly integrate to the B. Okay? So basically, if you have current density as a function of space, how to get B? And defining this vector magnetic potential A satisfies our need. Okay? Right? So now we have defined a new vector quantity. So basically, everything you need to understand about magnetic fields are right in front of you, right? You have current density. If you have currents, you can produce magnetic fields, right? Eventually, you will want to know B, but even though Ampere's circuit law is very simple and straightforward, but it's not very useful every time. Okay? So this equation is indeed true, but even though you have some known current density, you don't have a direct and easy way to know B. So we introduce A. Okay? So up to now, comparison between E and B, E fields are conserved, and we have defined an electrical potential, which is scalar. In the same analogy, we also defined a potential in magnetic field, but it is a vector. And B and A are related through a curl operation. So how to perform curl is extremely crucial, right? In order to master magnetic fields, you have to have the capability to perform curl operations, right? Physical meaning of vector potential A. So assume I have some area, right? I have magnetic field lines penetrating across this area. And we can just draw a circle, right? And we have the magnetic fields coming from our Earth. Our Earth is a big magnet, so we have fields penetrating across this area. So the area is S. Around it, the circumference is a closed loop C. So if we ask ourselves, well, if I want to evaluate the total number of magnetic field lines penetrating this surface, how should I do it? Simple and straightforward, right? This is called the flux, magnetic flux. The amount of field lines across the surface is called the magnetic flux. I only have to perform the surface integration of B, right? And therefore, B is called the flux density. If you perform the surface integration, that gives you the flux. But now that we know, through our definition, B is equal to curl of A. Well, it's following from vector null identity, curl of A. So if you have a surface integration of the curl of a vector field, that is reduced to the closed loop line integration of that vector itself. Again, this is using Stokes' theorem. And that's the reason why we covered divergence theorem, Stokes' theorem up front. Okay? So now what you can see is, if we care about the magnetic flux, we actually have two ways to calculate it. One is, I want to know phi b, I can perform the surface integration of b, or equivalently, I can calculate the closed loop line integration of A. So the meaning of vector magnetic potential A is you can get the same magnetic flux just by performing a line integration along a closed loop at the outer edges of your surface. Okay? So the physical meaning is apparent. By defining A, you can reduce your integration by one order, surface down to line. Right? So ideally, we're hoping, well, even though we have introduced a new term, but because the calculation involved is having one order of reduction, one dimension of reduction, so we might be able to find A directly from J. And then I perform curl of A to find B. Right? So this is telling you if the mountain is not turning, the road should turn. Right? 山不转路转. Okay? It's very difficult to find B from J. Let's give up. Let's try to reroute. Let's find A first, and then from the definition, curl of A gives B. We take the indirect path. Okay? So again, the need to define A is, even though the Ampere's circular law is coined here, but if you have the J known, curl operation of B equals to that, you don't have a direct way to find B. Okay? So we're hoping to introduce a new field quantity of A that could help us to land in B in a direct way with known J. Okay? But if you are a very strict person in terms of mathematics understanding, you would find, well, this definition is incomplete. Why? Because we have defined the vector magnetic potential A, the curl of it is equal to B, right? Our magnetic flux density. But if you want to have a well-defined vector field with a known curl value, it's only 50%. The other 50% to have a well-defined vector field comes down to the requirement you also have to know the divergence of that vector field. Right? So this is a simple mathematical issue. How should we define the divergence of A? Well, the divergence of A is really arbitrary. Because in the end, think about it. When we deal with math, we have to have a well-defined divergence of A and curl of A to have a well-defined vector field. But in the end, do we really care about the divergence of A? All we care about is curl of A, right? Because B is equal to curl of A. So essentially, course, the quantity of divergence A is not that important, right? So we are free to assume whatever value divergence of A is. Okay? That's our freedom. But to be complete, we still have to define divergence A to something. So in principle, although it's arbitrary, but we still want to define it so that A is completely defined vector quantity. So in reality, we like to have divergence of A equal to 0. Why? Because we're lazy. Something equal to 0 is simple and straightforward. Is that the whole reason? Oh, it's not because we're lazy. Think about it. Ampere's circuitous law tells you this, okay? And B equals curl of A. Does any one of you still remember the operation of double curl? We actually covered this. If you have a vector quantity and you perform double curl operation, that is equal to, this is actually the definition of the vector Laplacian, right? Divergence and then the gradient of the vector field minus the vector Laplacian. Okay. So now can you see why we like to define divergence of A equal to 0? Because we don't have to deal with the first term. This assumption is called the Coulomb's gauge. Okay? So even though divergence of A can take on any value, but if you specify to 0, it's called Coulomb's gauge. That helps us to find a direct path. Now think you're Columbus. You're trying to discover the New World. You're trying to discover India, but somehow you found America. Okay? So initially, from J, we want to land in B, but somehow we find it too difficult. We introduced A, and then we define divergence of A equals to 0, so we don't need to solve. We don't have to care about this term. So magically, it seems it's possible that if I know J, I can land in A directly. Right? So this is Columbus, and this is India, but this is North America. Beautiful. Okay. So let's come to this equation. Under the assumption of Coulomb's gauge, divergence of A equal to 0, we only have to solve Laplacian A equals to negative mu 0 J. So now, you have to think, this is really a major step forward. Why? Laplacian. What is Laplacian? Laplacian in Cartesian coordinate is just double differentiation, right? Double differentiation as compared to curl is still easy and straightforward. So now, by defining this A, it seems we have the potential to acquire A directly from J. We don't like curl operation, period. All this effort, we want to remove the curl operator. Right? So in Cartesian coordinate, Laplacian is for each component having its scalar Laplacian. Right? But it's still straightforward because scalar Laplacian is that component having double differentiation in all directions. Still manageable. Okay? Now, you might be puzzled. Well, after you you perform the Laplacian of A, you still have a vector, right? You still have a vector. You still have the x component, y component, z component. So that is equal to j. J itself is a vector. So even though you have 9 terms, 3, 6, 9, you have 9 terms, but you can group the results into 3 terms, right? By directions. In the x direction, y direction, z direction. So therefore, you come up with a set of 3 equations. So this is telling you, again, a lot of information. Your current density flowing in the x direction directly associates to the x component of your vector magnetic potential. Okay? And the y current density component directly determines a y, jz, ac. Right? So now the question is reduced to a set of 3 scalar Laplacian equations. That should be doable. Okay. All right. So this is something probably I omitted when we talked about electric fields. I skipped chapter 5 in Jen's textbook. But I'm trying to include the results. So this is called Poisson's equation. Okay? So this is fish in French. I try to learn the pronunciation, Poisson. Okay, this fish. At this point, we're trying to borrow the results from electric fields. This is a known equation, right? Divergence of E is equal to the charge density divided by the vacuum permittivity. But think, if we move this negative sign to the right, this is exactly what we're trying to work on. You have the scalar quantity and you have the Laplacian operator, which equals to a negative quantity. Again, I'm drawing a 1-to-1 correspondence between the E field and magnetic field. Right? So this is called the scalar Poisson's equation. Do we need to solve it? We don't really need to solve it. Why? Why not? Because we already learned Coulomb's law. Coulomb's law tells us, well, if you know the current density distribution as a function of space, you can try to find V. Right? So take a good look at this Poisson's equation. Even though I did not cover it, the reason is very apparent. If you know how to use Coulomb's law, well, this is not directly Coulomb's law, right? Coulomb's law is relating rho to E, but this is something we also derived, we covered. So once we know this relationship, the electric potential can be acquired by direct value integration of your charge density. This is a solution to the Poisson's equation. Okay? Now, what do we have to do to know the solution for AX, AY, and AC? Take a good look. For electricity and magnetism, basically you're solving the same equation in the same form. They're all called the scalar Poisson's equation. The only difference is now in magnetism, you are dealing with current density as a function of space. In electricity, you're dealing with the charge density. Second difference is in V, you have the vacuum permittivity in the denominator, but now in magnetism, you have the vacuum permeability in the numerator. That's the only two differences, right? So in the end, by introducing A, we have the capability to reduce the problem to solving three scalar Poisson's equations. And Poisson's equations have well understood solution form. One-by-one analogy tells us if we know the X current density component, then we now know the AX component of the vector magnetic potential. We only have to perform the integration, the volume integration, borrowing the solution form of our known electric potential. We replace rho by J, and we replace 1 over epsilon 0 by mu 0. That's it. This is a major step, a major leap, right? We can already know A once we know J. So we combine these three sets into one simple equation. The volume integration of current density divided by the distance multiplied by the vacuum permeability divided by 4 pi directly gives us A. Okay. So this is like finding North America. Right? You should be excited because given any current density distribution, we now can calculate A. Once A is calculated, we only have to perform this curl to arrive at B. But all the filming staffs in MIT AE do not look excited. Why not? Because they still call this byproduct. Remember, what is my overall pursuit? My overall pursuit is if given some arbitrary current density distribution, I can calculate B directly. Okay? So somehow you are the Portugal kings. You still remember the initial aim is to find India and not North America. Okay, you're good. You're smart. So we have to find a way to arrive at B directly by knowing J. Okay, that's the ultimate path. So even though we're already excited, by knowing J, you can arrive at A, but I mean, it's still A, right? It's a middleman. It's not the direct result. It's a byproduct. And if you are in this field early, even though you might not be so smart, you don't have a very keen insight into the physics, but you're very good in mathematical derivation, you can earn your name by doing that. Okay? So again, two French scientists, Biot, Savart, they did exactly the same thing. They probably went on a class and professor taught them, well, you land in North America, right? That's it. Once you have A, you perform the curl, you get B. So what they did exactly to use this form and perform curl of A. Okay? Curl of A. So once you have this A, you perform curl of A, you arrive at B. But in that process, after their solution, you find the direct path to arrive at B starting from J. Okay? So this is called the Biot-Savart law. Okay. They were thinking, initially, this integration is a volume integration. Remember, this is the volume integration for current density. If you think about it, you should be puzzled. Examination 1 and 2 is coming up next Monday. Right? What is current density? Current density is the surface density of current. So is there any meaning to perform the volume integration of current density? It's weird, right? Ideally, J is I divided by area. So J has a unit of amps per meter squared. So what's the physical meaning to have a volume integration? So to me, the major contribution of Biot and Savart was to realize, well, the basic current conducting element is a closed loop of wire. Okay? So you're trying to perform the volume integration of that wire, that closed loop formed by a wire, a conducting wire. So they somehow performed the integration, the volume integration. They reduced the volume integration into a closed loop line integration. How were they able to convert the volume integration, a three-dimensional calculation, down to a one-dimensional line integration? They realized the fact this loop is made of a conducting wire. So that conducting wire has certain area, right? So this volume integration can be written as the surface, which can be viewed as a constant, times the differential length. So differential volume is the area multiplied by the differential length. So J times S is equal to what? The current. So now the integration is really reduced to a one-dimensional integration, right? That's the major contribution from these two scientists. Okay. All right, so if we have some current conducting closed loop, we only have to perform the closed loop integration of the differential length. So again, if you still remember, I spent so much time teaching you differential length, differential surface in vector analysis for apparent reasons. in different coordinate systems, you need to know how to properly formulate differential length. Otherwise, you cannot master magnetism. Right? So here I have I. Okay? So if I know the current being conducted in a closed loop conducting wire, I can perform the closed loop integration to find A. But they were not satisfied just in knowing A. Just in knowing A cannot make you famous, cannot make you remembered. Okay? You have to do something else. You have to perform the curl operation. Because they understood the value to be able to directly achieve B from J. Okay? Oh. In another word, they want to have a counterpart of Coulomb's law. Okay? So up to now, I can say this is B. Let's set that. This BS is not that BS, okay? All right. So all you have to do is perform the curl operation. Then perform a direct and brutal curl operation. Then really perform the curl on A. So you have to respect them. My mathematical skill is not that good. I would never dare to perform direct curl on the generalized solution form. But for you to remember and understand, pay attention to how the coordinate systems are labeled. The prime, we are trying to perform the closed loop integration of the current conducting loop. We're always using the prime system to denote the source. Here, the source is a current conducting loop. But this curl operation is trying to perform the curl at the observation location, which means I have a current conducting loop which sets up some vector magnetic potential A at my observation point, right? So A in space is labeled by the unprimed system, but a current source is labeled by the primed system, okay? So this current loop generates some A distribution here. Once I know A here, I perform its curl. This curl operation, pay attention. Once I know A here, A is the result of the current conducting loop, which is expressed by the prime locations. But once I know A, I'm trying to find the resulting B by performing the curl. This curl is only depending on my observation point. It's no longer associated with this current loop. So this curl operation is only operating on the unprimed system. Okay? Why do I care so much? Because this dl prime means the differential length, differential segment on the loop, right? So this curl operation now operates on 1 over r. 1 over r is the distance vector, right? Which is sensitive to both the unprimed location and the prime location. The prime location means x prime, y prime, z prime to denote a space, a point on the current loop. So by now, I have curl operation on 1 over r times the differential length on the loop. So basically, these are two different quantities. This is a vector, 1 over r is a scalar. So I have to borrow the vector identity from the textbook. Okay? So if I perform the curl operation on the multiplication of a scalar and a vector, that can be decomposed into 2 parts. That's fine. Whenever I add complexity, I find functionality, right? So I have a new form, but look at this equation. You should be very happy because if we know current, hey, it guarantees us to arrive at B directly after some mathematical manipulations. But we have 2 terms from the vector identity. Now, smart students like you would understand why I emphasized on the primed system and the unprimed system. The curl operation operates on your observation point. It does not care about your source coordinates. So this curl operation, does it affect dl prime? dl prime is the primed location. It does not really care about it. But this gradient does operate on 1 over r. Okay? So basically, this term can be dropped. This is the desired result. Okay? So in the future, if we know the current in the form of a closed loop, all we have to do is we perform the closed loop integration of the gradient of 1 over r, making a cross product to the differential length on the conducting loop, and multiply by this. So this is the direct way to knowing the current arriving at B. Okay? But Biel and Sabat does not earn their name by stopping here. Okay? They earn their name by knowing, well, in Cartesian coordinate, 1 over r is this, right? Your observation point minus each differential segment, right? The sum of the square, and you take the square root, that is the distance r. Now, how to perform the gradient? Gradient in Cartesian coordinate is just direct differentiation to x, y, and z. Right? That's what you have. Basically, in Cartesian coordinate, gradient of 1 over r is equal to the negative of your distance unit vector divided by the distance squared, or the distance vector divided by the distance cubed. So now this is, and then dl cross gradient cross dl is negative dl cross this, right? So this is the Biot-Savart law. You have 2 forms depending on how you write this term. These 2 are equal, but you can say this is the unit vector divided by r squared, or the vector divided by its distance cubed. Okay, so you have 2 forms. Once you know the basic current conducting element geometry, all you have to do is perform the closed loop integration you arrive at B directly. Right? So let me copy this result for you. So we spent so much time eventually our initial motivation was to be able to calculate B field by knowing the current distribution. But Ampere's circular law is difficult to use. I mean, if your current distribution is arbitrary, non-uniform, right? So somehow, invoking mathematical null identity, we define A. A is, the curl of A is equal to B, right? And then we started to solve. And we came up with 3 sets of scalar Poisson's equation, and we combine them into this one. So this is telling us, well, if you know the current density distribution, we can find A first, and then perform its curl to get B. But Biot-Savart saw the possibility to really operate curl on this generalized form. Okay? So in the end, magnetism has a one-to-one counterpart to electricity. Ampere's law compared to Gauss's law, and now Biot-Savart compared to Coulomb's. Okay. Now, this is a better side-by-side comparison. What is Coulomb's law? Now, in the past, we spent a lot of time, right? Coulomb's law tells you, well, even though we know that in real life, for electricity, we have the E field and we have the electric potential V. But once we know the distribution of the charge density, using Coulomb's law, we are able to arrive at the E field intensity directly without the need to know V. So V can be viewed as a byproduct, North America. And this is E here, right? At the same time, for magnetism, I together with dl prime, this is a differential segment on your current conducting loop. So together, you know how your current is formed. Using Biot-Savart relationship, you can directly know B without the need to find A first. In a one-by-one analogy to electric field. Okay? So the main contribution of Biot and Savart is, well, even though we defined A, but A is pretty superficial, even though we understand the physical meaning of A as compared to B, B you have to perform a surface integration to find the magnetic flux. A, you only have to find a closed loop integration, but still, it's not so direct and not so straightforward, right, to understand A. So they are saying, hey, even though it's there, let's forget about A. So in the future, whenever you have current, we find B directly. That's it. Okay? So in my personal opinion, I think the ability to calculate A or not is really up to you. Okay. A is really not that well defined. As we mentioned, divergence of A can be chosen arbitrarily. So the meaning of A is really, vague. Okay, it's there mathematically because we want to be able to solve B directly from current. Okay. So let's stop here unless students have questions. Well, if not, I'll see you on Wednesday. And next Monday, please enjoy your examination. But the examination will be, you need to come to the classroom, right? So I will send out another notice using email to you. All right, thank you.